So here is the question we have. We have to find the inscribed and superscribed circles radii for a triangle with sides 7, 7, and 4 units long. Let us notice that this is an isosceles triangle. And because of that, we can solve this using just the Pythagorean theorem and understanding radicals. Well, both parts. Let's see how that goes. So, as always, I think that realistic picture is helpful. And this would be the 7, 7, and this would be the 4. Something like that. Now let us notice that because the triangle is isosceles, this line is a perpendicular bisector and also an angle bisector. It's a complete symmetry line. This picture is symmetrical to that line, which means that this side is 2. I mean, these right triangles, and this side is 2, and the other line segment is also 2. Basically, this altitude splits the opposite side into 2 halves. Now we can find the altitude of the triangle just using the Pythagorean theorem. If we call it h, h squared plus 2 squared equals to 7 squared. So h squared is 49 minus 4. So h is square root of 45. Or its opposite, but of course, h has to be a distance, so the negative solution is discarded. And we can simplify root 45 as 3 times square root of 5. As we walk into the problem, we don't really know which form is going to be more beneficial to us. So it's just best to have them both. All right. So now we're ready. This here is the radius of the superscribed circle. And so is this. And so this side here is R. And this is also R. And the big trick is going to be, we're going to state the Pythagorean theorem on this triangle. Now this side here is square root of 45 minus R long, right? This whole thing is square root of 45 and this is R, so this is what's left. So it's a little bit more visible. This side is 2, this side is square root of 45 minus R, and this side is R. And off we go, we state the Pythagorean theorem for this triangle. 2 squared plus square root of 45 minus R squared equals to R squared. Now, I don't know about you, but if I have to square this or this, I actually prefer this form. So because there is a complete square here, we're going to have to square this number. I use the original form, not the simplified one. So we have 4 plus 45 minus 2 square root of 45 times R plus R squared equals to R squared. And not only this is an equation in just one variable R, but if you notice, it's linear in them. So there's going to be one unique answer. So we have 49 equals to, and I'm going to simplify now. So we add this to both sides to basically bring it over to the right-hand side. And then we have 2 times. And now instead of root 45, I'm going to use this 3 times root 5. Root times 2 times square root of 45 R. And to solve for R, we're just going to divide by whatever is multiplying capital R. And that's 6 root 5. The problem is asking for an approximate value. So we're just going to punch this in. But you have to be careful to enter exactly what you mean. 49 divided by, and I'm going to open a parenthesis, 6 times square root of 5. Now the square root opened a parenthesis for you. We have to close that. And we got approximately 3.652244. I rounded up 36 to 40. we're asked to approximate up to 4 digits, so that would be this part. 3.6522. All right. Now for the inscribed circle. The solution is going to be surprisingly similar. Now the inscribed circle is such all three sides of the triangle are tangent lines to the inscribed circle. And how do we use tangent line to a circle? Well, the radius drawn to the point of tangency is perpendicular to the tangent line. So there is a right angle here. You remember that if you have an external point, from that the two tangent lines reach the circle at the same distance. So these tangent line segments are equally long, which means that this here is 2 and this here is 7 minus 2 or 5. And this is little r, and so is this here, and this here is the height minus little r. So that side is going to be the height, which is still square root of 45 minus little r. And so we're going to be able to solve for r very similarly if you just state the Pythagorean theorem on this right triangle. And all the computation is going to be similar, you will see. So what we have is r squared plus 5 squared equals to square root of 45 minus r squared. Right, the hypotenuse is always the one opposite the right angle. So we have r squared plus 25 equals to 45 minus 2 square root of 45r plus r squared. R squared cancels out, and we are left with a linear equation again. We're going to add to both sides this to bring it to the left-hand side. So we're going to get 2. And again, instead of root 45, I'm going to say 3 times root 5. And then we subtract the 25, we get 20 on the other side. So what we have now, r is 20 divided by 6 root 5. Between 20 and 6, there is a 2 that they share, so that's 10 over 3 root 5. But actually, 10 is 2 times 5, right? And 5 is square root of 5 squared. So we don't have to artificially rationalize if we just notice that 5 is root 5 times root 5. So then we get 2 root 5 over 3. It's not a big deal, but actually this one has more danger about entering it into the calculator than this. And also, if we are asked exact values, then this is the number to give. We could have multiplied upstairs and downstairs by root 5, and then 5 cancels out, and we would have been left with this expression. So if we are asked for approximate values, let's see, we just enter this. 2 times square root of 5 divided by 3, and we get is 1.490712. If you round that 19 up to 20, that feels like a compromise I can live with. 1.490712. And the units were not given, just units. So let's check. That's always fun. If we enter our answer, so the inscribed circle's radius was 1.4907. I stop here because if you notice, we are asked to round the answer to 4 decimal places. And then the bigger circle, the circumscribed circle, has a radius of 3.6522. After the 2, there's a 4, so we're rounding down. Now let's see what happens when we submit this. Both are correct, so we got it right. Thank you for watching.